For the longest time, we believed that creative tasks like composing music, designing fashion, or writing poetry could be only done by humans. But that assumption has been completely shattered as we are now going through a revolution that powered by computational techniques that can generate brand new meaningful content, be it text, images, or even audio, all learned from its training data. I am Sumit Kumar Das and welcome back to SKT Neural. Today, we are deep diving into how generative AI, that is one of the most transformative technology of our time, become an essential part of our daily lives. Before deep diving, if you are new to the channel, smash the subscribe button and hit the bell icon so you don't miss the upcoming ones. But to really understand this transformative tech, we need to break it down through what I call a sophisticated socio-technical lens. We are going to explore generative AI across three interdependent levels: the model, the system, and the application. So let's start with the level 1. Level 1 is all about the model. This is the core machine learning architecture. At this level, we are usually dealing with deep neural networks that use AI algorithms to create brand new data instances based on the patterns they have learned from its training data. These deep neural networks are perfect for this because they can be designed with different architectures to handle different types of data. For example, sequential data, that is human language, or spatial data, that is images. Models like GPT-3, that is a text generation model, or Stable Diffusion, that is a image generation model, these all exist at this level. Now let me introduce to the something called as foundation model. These are massive generative AI models that can generate output across specific domains or data types in a really comprehensive way. But what makes them special? Two key properties: emergence and homogenization. Emergence means the model's behavior is often implicitly induced rather than explicitly constructed. For example, GPT models can generate calendar entries in the ICL format, even though they were never explicitly trained to do that. And homogenization means a single consolidated model can power a wide range of system and application. For example, take GitHub Copilot. It can generate source code across tons of different programming languages, all from coming single one model. Now, we can also categorize these models by their modalities as well. Unimodal models take instructions and generate output in the same type, like text to text. But multimodal models, on the other hand, that can take input from different sources like images or text and can generate output also in various forms. Example: Stable Diffusion, that is text to image generation, or music LLM, text to music generation, and GPT-5 that can accept both text and image inputs and can generate also both text and image output. Moving on to level 2, the system. A generative AI system contains the entire infrastructure. We are talking about the model itself plus data processing like handling prompt or user facing components and the user interface. The system embeds the model functionality to provide an interface where users can actually interact with it. This augments the model's capability and make it practical and usable in real-world scenarios. Think about GitHub Copilot. It integrates the codex model into a system, or Midjourney, which uses an text-to-image model that users interact through a Discord bot. When designing any system, developers have to address core concerns like scalability, like think about distributed computing resources, the deployment across different environment and usability. Think about the massive adoption of ChatGPT that was largely driven by how easy it was used to use, even for people who are not tech expert. Here is something important. The system level can actually mitigate known limitation of the model. Since many models are trained on historical data with a specific cutoff date, the system can be enhanced with functionality for real-time information retrieval to improve the accuracy. There is also something called as online language modeling that can be used at the system level to continuously train models on up-to-date data, ensuring they are knowledgeable about recent events. Finally, we have level 3, the application. This level is all about practical use cases and implementation of generative AI system within the organization. These applications deliver value by solving specific business problem and addressing stakeholder needs. Think of them as human task technology system that augment human capacities to accomplish specific tasks. The applications are incredibly diverse. We have seen generative AI used for content generation, AI music generation, synthetic movie generation, or natural language based software development as well. It can even assist transitional knowledge work tasks like supporting IT help desk. And here is where it gets really interesting. Over the time, these applications are expected to transition from boring tasks like writing standard letters or getting dinner reservations to more sensitive tasks like providing medical or legal advice. Now, to understand how generative AI actually creates content, we need to look at the underlying mathematics, particularly generative modeling, that aims to infer the actual data distribution such as the joint probability distribution of inputs and outputs that allow to produce new synthetic sample. And there is a different architecture also called as discriminative modeling that aims to separate data points into different classes by learning decision boundaries, like in classification task. Let's break it down. First is large language models or LLM from generative modeling. These are neural networks designed for modeling and generating text. They combine three key characteristics: a large scale sequential neural network like transformer, and a pre training through self supervision like next word prediction, and the use of massive text datasets like Wikipedia. The transformer architecture is essential here because it uses a self attention mechanism to differentially weigh the importance of each part of the input data. Large language models like GPT-3, which has approximately 175 billion of parameters, are few shot or zero shot learners. That means they require only a few sample or sometimes no sample at all to learn a task. The second critical architecture is generative adversarial network or GAN that is based on discriminative modeling. A GAN involves two neural networks competing in what's basically a zero sum game. You got the generator, let's call it G, which creates candidate samples. Then you have got the discriminator, that's D, which evaluates how likely those samples came from the desired true data distribution. These adversarial objectives help the generator learns to map random input to a data distribution of interest. It's like a forger and a detective constantly trying to outsmart each other. And in this process, the forger get better and better. Conversational models like ChatGPT use something called as reinforcement learning from human feedback or RLHF. This training process happens in three steps. First, creating demonstration data for prompts. Second, having human users rank the quality of the different outputs for a prompt. And finally, learning a policy via reinforcement learning to generate output that scores well during ranking. This ensures that new answers align with predefined human preferences like style or appropriateness. We have also seen the rise of the prompt learning. This is a method for large language models that uses specific input prompt to leverage the knowledge stored in the model without requiring resource intensive fine tuning of the model itself. And in the recent time, focus has been shifted to data driven prompt engineering, sometimes even using reinforcement learning to tune the prompt for optimal results. Now, as impressive as all this sounds, current generative AI systems face significant technical boundaries that impact real-world applications. These limitations often arise at the model level and persist throughout the implication at the system and application level. Let me walk you through four major boundaries. First is incorrect output, also called as hallucination. Since these models rely on the probabilistic algorithm for making inferences, they generate the most probable response to a prompt, not necessarily the correct one. In large language models, this problem is called as hallucination, where the generated text is semantically plausible, it sounds right, but it's factually incorrect. And the output is often not easily verifiable, which poses a critical problem for users trying to trust the content. The correctness of the output critically depends on the quality of the training data and the learning process. A potential solution is using generative AI to produce probabilistic explanation or references alongside the output that help users make informed judgment about when to accept the model result. Second is bias and fairness. Generative AI models are highly dependent on the quality of the training data and the alignment process. Training deep learning models on biased data can amplify existing human bias, replicate toxic language, and perpetuate stereotypes based on gender, religion, or political learning. Biases can also come from initial training data, like those found in datasets used by multimodal models like DALI 2 or Stable Diffusion. Additionally, the RLHF process used in instruction based language models is another source of bias. While addressing bias is still an ongoing research question, mitigation mechanism can be implemented at the system and the application level. Third is copyright violation. Generative AI system pose two primarily intellectual property infringement risks. First is they may violate the reproduction right of creators by making illegal copies of copyrighted work, often because they are trained on the protected content. Second, they may violate the transformation right of creators by preparing their derivative works. And here is something important. Infringement may still occur even if the generative AI has never seen the original work, like unintentionally producing a trademark logo. This raises complex legal questions around the balance of originality, creativity, and who actually holds the intellectual property, including patents for AI generated works. And fourth is environmental concerns. Generative AI systems which rely on large scale neural network requires immense energy consumption for both development and operation, resulting in a substantial negative carbon footprint. For example, the carbon emission generated during the training of model GPT-3 was estimated to be 552 tons of carbon dioxide. Ongoing efforts in AI research are focused on reducing this impact through more efficient training algorithm, native architecture compression, and optimized hardware. But it's still a significant concern we need to address. Alright, let's wrap this up. Generative AI is a powerful branch of AI that can create new content. And also, we saw how this technology functions across three critical levels: the fundamental model, the enabling system, and the practical application. While generative AI offers unprecedented potential for transformation and innovation in domains relying on creativity and knowledge processing, its effective use depends on entirely on managing those limitations we discussed: hallucination, bias, copyright risk, and environmental impact. Understanding the distinction between the model, the system, and the application is key to manage these socio-technical challenges and ensuring responsible engagement with this revolutionary technology. So, what do you think? Let me know in the comments below. And if you found this deep dive helpful, smash the like button, subscribe to SKD Neuron for more such AI breakdowns, and hit the bell icon so you never miss an upcoming video. See you in the next one. Till then, keep learning, keep coding, and keep growing.